All right, I want to begin today by talking about some of the homework problems from the homework assignment the last time we were together before we go on to the new lesson. For these problems up here on page 2 of the homework assignment, you don't have to do the algebra steps in the order that I chose to do them, as long as you can solve for the variable. That's all I want to say about that. Let's see, moving down, I'm more concerned really about problems 6 and 7 here. For number 6, again, one of the strategies that I recommended, actually I think the only strategy I recommended, was come up with a rectangle and dimensions that would produce this area here of 6,000 square inches. Now, there's lots of choices for that, but dividing by 100 seemed like a fairly obvious choice to me. And if you create a rectangle with 100 by 60 inches, could you get a little closer to the square? Maybe. And that's always a good idea. But 60 inches by 100 inches is easily converted to feet, dividing each by 12. You get 5 feet by 8 1/3 feet. And of all of the choices that you're given here, I think a bed blanket seems far and away the most reasonable choice for that area. For number 7, I use the trapezoid formula here. One of the bases was given as 45. The other upper base, CD, had to be found because it was not given. And also the height of the trapezoid had to be found. So I drew a right angle there, an altitude there, used this 30, 60, 90 triangle to find this height of the trapezoid, which would be half of that hypotenuse there, 10. And then this longer leg is whatever the short leg is times the square root of 3. 10 times the square root of 3, that's about 17.3, something like that. And if you subtract that from this 45, you'll get the length of CD up here, 27.7 approximately. So then I had the length of the upper base to be 27.7. I had the length of the lower base that was given, 45. I found the height of that trapezoid and calculated the area that way. Now you are perfectly welcome to find the rectangle area and the triangle area separately and then add those areas together. You should get the same result. Trapezoids can always be divided into a combination of rectangles and triangles. In this case, one rectangle and one triangle. But if this side of the trapezoid over here were also at an angle and not, at an angle that was other than 90 degrees, we'd have a triangle on that side also. So I think sometimes cutting it into a rectangle and a triangle or triangles can be perhaps a little more work than just using the trapezoid formula, but I don't care if you want to do it that way. It's totally up to you. Let's look at couple of problems on page 3 of the homework. Again, just really more algebra here at these problems at the top of the page. If you found this one to be difficult, I'm going to say don't worry. I'm not going to discuss it because this is largely what we're going to be talking about in today's lesson. And then converting areas from one unit to another. Here's one way of doing it. For these problems, I did have two ways. Two suggestions for how to do it. One way is come up with a rectangle with dimensions that would produce 500 square feet. Convert each of those to yards. If there's 3 feet in a yard, we're going to divide the number of feet by 3 to find the number of yards along each dimension, and then multiply those yards to get square yards. Another way to think about it is if you would ordinarily divide feet by 3 to get yards, then you would divide square feet, not by 3, but by 3 squared to get square yards. So instead of dividing 500 by 3, if you just divided it by 9, that would produce this result immediately. Likewise down here with problem number 12. Let's talk about the way to do it other than the way I showed here. How would you convert feet to inches? If you had, 5 feet, how many inches is that? I think you all know you'd multiply by 12. But if we're going to convert square feet to square inches, we're not going to multiply by 12. We're going to multiply by 12 squared, which is 144. So if you multiply 60 by 144, you'll get this answer immediately. But the other option is just to create a rectangle, really with any dimensions at all, that would produce 60 square feet. Convert each of these linear measurements into inches, and then multiply the inches back together, and you should get the same result. If you have any other questions about this homework assignment, feel free to email me or communicate with me somehow. And you can include pictures if you want, or a description of your work, and I will be happy to try to resolve any other questions or confusion you have about those kinds of problems. Let's move on to today's lesson. I'm going to go through these lessons more quickly on video because you have the opportunity always to pause them and review them. So I'm not going to include those pauses in my creation of the video like I do when I'm just presenting the material to you. So here's an equilateral triangle. And I'm just going to follow the steps prescribed at the top of the page here. Draw an altitude from A to BC. An altitude by definition forms a right angle. I'm going to call that point L. That's what it tells me to do up there. And again, triangle ABL, if this is coming from an equilateral triangle, that would be 60 degrees. Since we made that to be a right angle on purpose, we've got a 30, 60, 90 over here. I'm calling AB X. So how long is all of BC? Well, it's the same length as AB. We call that X. And so how long is BL? Well, it's going to be half of BC. So it's going to be 1/2 X, or X over 2. And then the length of BL, well, in a 30, 60, 90, I'll remind you that 2, 1, and square root of 3. Here's our relationships among any 30, 60, 90 right triangle. The long leg is always the square root of 3 times whatever the short leg is. Our short leg is 1/2 X. Take that and multiply by square root of 3. 1/2 X times the square root of 3. And you've got the long leg. Okay. So now, what I want to do is come up with an expression for the original equilateral triangle ABC. It's 1/2 times the base times the height. Now the base of this equilateral triangle, we're just calling X. The height of this equilateral triangle is 1/2 times X times the square root of 3. So there's the 1/2 from the formula. That X represents the base. That 1/2 is part of the height. So now simplifying this result, again, all these things are being multiplied together, so it doesn't matter what order we multiply them in. 1/2 times 1/2 is 1/4. X times X is X squared. And then we have a radical 3. I'm going to treat the radical 3 as if it was a fraction. Square root of 3 over 1. Multiply that by this fraction and get square root of 3 over 4. And then I'm also going to treat the X squared as if it was a fraction and multiply the numerators, which turns into X squared radical 3 over 4. So there is an expression, or if you will, a formula for the area of any equilateral triangle if you know the side length. And suppose we call the side length S, S for side length. Then formula for the area of any equilateral triangle, would be S squared times the square root of 3 and divided by 4. I will give you that formula on any quizzes or tests. I'm not going to say that's formula for the area of an equilateral triangle, but I will write it just like this. A equals S squared radical 3 over 4. It's going to come in very handy on tonight's homework. It probably would have made one of the homework problems from the last assignment quite easy. If you know the length of a side, you just plug that side length into this formula, you're done. If suppose the side length was 10, 10 squared is 100, 100 divided by 4 is 25, and so you'd have 25 times the square root of 3. End of story. It's a very quick problem if you know the side length of an equilateral triangle. Let's go to page 2 of the notes. And again, these completed notes are posted or will be posted immediately after I post this video. And so you can see a completed copy of those if you're not trying to record these as we go. Here I've got a regular octagon. Regular. Okay, so all of the sides are congruent. You recall that's the meaning of the word regular. All right. If it's regular, then it could be divided up into 8 triangles that are all congruent to this one here. This one triangle uses one side of the octagon as its base, and we could create 7 more triangles going around the octagon congruent to that. So the idea here is that if we can find the area of this one triangle, then we could just multiply that by 8, and we'd have the area of the entire octagon. So we're going to call one side of the octagon S for side length, just like we did for the equilateral triangle. S is going to stand for side length. And then from this center point of the octagon, if you will, drawing a line at a right angle to a side of the octagon, I'm going to call that A. And the reason I'm calling it A is because this distance, as it says over here, from the center of any regular polygon, doesn't have to be an octagon, to the side of the polygon at a right angle, it's called the apothem. That's how you pronounce that word, apothem. So the area of a triangle, of course, is 1/2 times the base times the height. We're calling the base S for side length. We're calling the height A for apothem of the original octagon. And so the area of this one triangle is 1/2 times S times A. But of course, there's 8 of those triangles. So the total area of the octagon would be 1/2 times S times A times 8. Of course, we could simplify that by multiplying the 8 and the 1/2, but I'm going to leave it like that for right now. Let's go on to imagine that we had a decagon, 10 regular or 10 congruent sides in a regular decagon. We could take the same approach in creating an expression for the area of this regular decagon. Let's just find the area of one triangle. There's 10 of them. Well, that one triangle would be 1/2 times its base, which is S for side length, times its height, which is A for the apothem. So 1/2 times S times A. But there's 10 of those triangles. Okay? So this number changes depending on the number of sides in the polygon. And what we want is a formula that we could use for a regular polygon of any number of sides, where this could be 8, 10, 20, 1,000, whatever. So we need a variable for that value that stands for the number of sides in the polygon. So we're going to use the letter N for that. And so the area of a regular polygon, that's what that REG stands for, is 1/2 times the side length times the apothem times the number of sides in the polygon. And again, I'll give you that formula on all quizzes and tests. Right? We could use that formula for the regular hexagon or the regular octagon or a regular decagon or a regular anygon, really. Okay? But the thing about a hexagon is that a hexagon's triangles, that one triangle there, which I'm going to call A, B, C, that triangle is an equilateral triangle. And we have this formula for equilateral triangles. We could use this formula also, 1/2 times the base times the height. We could use either one of these formulas if we had the right information. If we have a side length of this regular hexagon, then we can just plug that into here. And then really, in my opinion, it would be a waste of time and effort to use this formula because the base of this triangle is the side length. And using this formula, that's all we need. To find the height, we'd have to do some more 30, 60, 90 work. So I don't know why you would ever want to use this formula if you could use this one when you had the side length. But there will be some homework problems tonight where I'm giving you this distance here and not the side length. So you will have to do some 30, 60, 90 triangle work to determine the side length if I've given you the apothem of that regular hexagon. And at that point, you could either use this formula or that formula to find the area of that triangle and then multiply by 6. But if it were me and I were given the side of a regular hexagon, I would not go with this formula here, 1/2 times s times a times n, because I would have to do some work to find the length of the apothem of that regular hexagon. If it's a regular hexagon and I'm given a side length, I would use this immediately to find the area of one triangle, and then I would multiply that by 6. If you forget about sort of that easy opportunity to find the area of a regular hexagon, and you do the 30, 60, 90 work, and you use this formula, that's, again, fine with me. As I always say, it matters very little to me ever what method you use to solve a problem, as long as you can show me what you're doing, make it clear, and it is mathematically legitimate. So I think that will do it. Just one last reminder here, be careful. This area formula is only for equilateral triangles. And in regular polygons, equilateral triangles can only be carved out of hexagons. Let me take you back up to these pictures up here. This octagon can be carved into 8 triangles. They are not equilateral triangles. This decagon can be carved into 10 triangles. They are not equilateral triangles either. Only in the hexagon, when you carve it into 6 triangles, do you get equilateral triangles. So with other regular polygons other than hexagons, you pretty much have to use this formula. Or at the very least, this formula to find the area of a single triangle. And then you've got to remember, I got to multiply that by the number of triangles that there are. So I think that's it. The homework is posted, and my work and answers are posted also. Good luck with that. Email me with any questions, and I'll have a new lesson posted for tomorrow.